Okay, in this video, we're going to take a look at problem 7.62. And this is another problem that involves a hypothesis test. For ESP. Now keep in mind that the hypothesis test, written in English, for any of the ESP type problems that we've been doing would be that the subject is just guessing, or we might say does not have ESP. And of course, when we say ESP, we're referring to extrasensory perception. The alternate hypothesis, which I like to call the researcher's hypothesis, is that the subject does have ESP. In this example, there is an experiment, and the experiment involves 5 cards, and each of the cards have a different shape. And in this example, well, let me say also while I'm talking about the 5 cards that one card will be correct out of the 5, and one card will be or 4 cards, I should say. 4 cards will be incorrect. So we have one way of having a success in this experiment and 4 ways of having a failure for a total of 5 possibilities. So that means the probability of success would be 1/5, and the probability of failure or not being successful would be 4/5. And this information is going to become important because in Part A, we're asked to define the hypothesis in terms of P, which is related to the actual proportion of correct guesses the subject would get if they were just guessing. And sometimes, just to be clear up here, let me write guesser here, ESPer here, because sometimes when I talk about this problem, I refer to the guesser hypothesis and the ESPer hypothesis. All right, what other details can we glean from this problem here? How many trials will there be in this example? 96. So the subject's going to be given 96 attempts. And as I'm thinking about this, I'm realizing also that this situation is a binomial situation. And in fact, let me define the variable as the number of correct guesses. And of course, this is the number of correct guesses out of 96 attempts. All right, let's see. So I think we're ready for Part A. And in Part A, we're asked to state the statistical hypothesis using the parameter value. And we're more and more in this class now from here on out, we'll be stating the null and alternative in terms of and it really what I would say is a more mathematical way using parameters. And in this case, the parameter is P. That's the true proportion of correct guesses our subject would get. Or actually, well, we have to be a little bit careful here. We're talking about the whole population of people, and this is their proportion of correct guesses in this experiment. If we selected people at random, P is what we would expect them to get correct, the proportion. And so for the null hypothesis, this one, we're assuming, again, the person's a guesser. And what we have to realize is that true proportion, if the person's just guessing, is going to be 1/5, and 1/5 is equal to 0.2. Now, if the person's an ESPer, then we would expect them to be getting a higher proportion correct. And so we would say then that the true proportion is greater than 0.2. And so what we're going to really be trying to figure out here is how far does that data value have to land in the data set when we do the experiment on our subject away from 0.2 and in the direction of greater than 0.2 in order for us to start to believe it's a rare and unusual enough event, to quit believing the null is true. So in part B, we're asked to find a p-value. And again, one of the very widely used measures of statistical significance in really anywhere in statistical research. So calculating the p-value is going to be an important thing. Now, we have calculated p-values in the past for similar problems using simulations. So I could approximate the p-value as we have in the past using simulations or using a simulation. This one's going to be quite difficult though, because the sample space for this situation goes from like 0 all the way up to 96. And so if I were going to try to draw an axis here and start thinking about how I would create a frequency plot for the distribution in this situation, this is going to be a huge challenge. And I'm just kind of messing around down here showing you how difficult it would be to scale an axis such that we would have scaling all the way up to 96 here. However, I think it's worth a minute or two to show you that we could use the calculator program from the ESP activity to simulate the same situation that we have here. And so let's see, I'm going to go ahead and run this program. Now, the Guesser distribution here, what I'm calling the Guesser distribution, is going to be 1, 0, 0, basically 1 with 4 zeros. And in the ESP activity, you use playing cards, and so there were only 4 suits that we were considering. So we had 0 or 1 and 3 zeros. But in this experiment, we add a card, and there are 5 cards. So I add another 0. Now what this represents is 1 way for a successful guess and 4 ways for a false guess or an incorrect guess. Next, we input the number of guesses. That's where the 96 comes in. Now, on the activity, I was only having you do the experiment with 10 tries rather than 96. So this is quite a bit more. And I'm not going to do a whole bunch of repetitions this time. I'm just going to go for 10. And so you can see what's happening here. The calculator is printing out different x values, and I get a range of kind of common x values here. And again, I'm going to go ahead and look at this in the list editor, these responses, because remember that the program saves all of the simulated x values in L5. So what I'm seeing is, there's an 18, an 18, a 25, a 12, a 16, and those would all be kind of clustering down here along the axis. But again, I would have to run this program so many times to really start to get a good idea of what the p-value is. In a way, I mean, again, I want to say it's impractical, but if you were programming, if you wrote a computer program on a fast computer, you could actually do this simulation and get pretty good results. But given that the TI calculators are, not supercomputers or anything like that, they're slow, they have memory issues. So yeah, we're kind of at our limit with this problem using the calculator. For simulations, that is. Now let me come back to this problem here for a minute. So let's review real quick. I lost trying to get back to my green screen here. I lost what I had written before, but let's go ahead and let me kind of sketch back out the situation here. Here's our statistical hypothesis in terms of p. And now we're talking about p-values. And we were just talking about how we might simulate an estimate, but we're going to do what I call, sometimes I refer to this as the theoretical p-value, and refer to the simulated p-value as like an empirical p-value. But in any case, we're gonna use math theory to calculate what the p-value should be, or actually is. Now, in order to calculate a p-value, we need three things, or we need to consider three things. What I like to call the null distribution. And in this case, this is a binomial with 96 as n and 0.2 as p. So this is the distribution that we'll be using for making our calculations. We also have to consider the direction of extreme. And in this case, we have a direction of extreme that's one-sided, and it's to the right. And to understand that, we can go back to our hypothesis and see that the x values in this distribution, and remember x is the number of correct guesses, the x values in this distribution, larger values are going to be more common when we consider the alternate hypothesis when compared to the null hypothesis. That's why we say the direction of extreme here is to the right. And the third thing we need is we need data. And really what this is, it is our statistic, our data value, our value from the data. In future iterations of this problem down the road, we'll be talking about p hat. And I'm just going to kind of put it here to foreshadow that. Right now we're looking at just x values, but p hat is a statistic. It's a variable. Depends on the sample size and the x. So we could we'll do this problem or a similar problem down the road, and we'll be doing it in a different way. But for now, we're just focused on the x value. Now, the data that was given in this problem was that the subject got, let me double check this. Yeah, 35 correct. So the x value is 35. Now the probability, or I'm sorry, the p-value, which is called the probability value, the p-value is equal to the probability of sampling the observed value. That would be x is equal to 35. And also all the data values greater than 35. So it's the probability of the observed value plus the probability of all the more extreme values. And since the direction of extremes one-sided to the right, that's where the greater than or equal to comes from here. Now, to calculate this p-value using the calculator, we need to recognize, based on the complement rule, that, and again, and how normal CDF works as a less than or equal to here. See, that's greater than or equal to, so I can't just use binomial CDF directly. I have to use the complement rule, which is 1 minus the probability. And I have to think about these inequalities and how and what number to put here. So the number I put here is one of the trickier parts of this problem. One thing I do when I'm doing a problem like this to try to figure out how to get that inequality right is I think in terms of like a giant tree diagram here, and it's sort of a framework. It's one way I could represent the binomial PDF in this situation, the probability density function. So on the left side here, I'm just going to put possible values for x. So the subject could get none right, 1 right, 2 right, up to 3 right. And I'm going to put an ellipsis here. So that pattern would continue. Because all of these values here, I mean, they're going to get swept up into a cumulative calculation at some point. And so I want to think in terms of the numbers down closer to where the data value is, like 33, 34, 35 is the actual data value. Oops, 35 is the actual data value, and 36 would be the next one, and then 37, and so on. Doesn't really look like a 5, but all right, 35. Now, this is the data value, so that is the actual x value that was sampled. And the p-value is the probability associated with all of these numbers. Now, I'm going to continue this table just to kind of give you the full picture, but, oops. And then we could maybe jump in at 90, 4, 95, 96. So the p-value would represent the sum of all of these probabilities on this side over here. All of these probabilities. So if we had a function on the calculator that would just let us find that sum directly, the sum of the probabilities from 35 all the way down, because again, the direction of extremes to the right, so the numbers are getting bigger in this direction. So this would be the p-value. We do have the ability, however, to calculate the cumulative probabilities from starting at 0 and moving down through here. So the cumulative probability, or the sum of all of these probabilities, is given directly by binom CDF. So in this particular example, if I typed in binomial CDF 96.234, what the calculator would return is the sum of these probabilities. So knowing or realizing also that the total of all of these, the total probability mass, as we say, is going to be 1. So if I take and subtract binomial CDF with all of these parameters in there and subtract that from 1, I'm left with the p-value. And that's the structure I have right here. And so now I can see the number that I need to write here is 34 from right there. So in any case, I find this diagram useful to keep straight, to make sure that I've got the right number here when I'm dealing with these inequalities. And I'm just going to write out what we would enter into the calculator now to calculate this, and then we'll do the calculation. All right, so let's get the calculator back out. Just pressing clear here. I did second quick because I was in the list editor, and then clear to clear the screen, just to get rid of the clutter. 1 minus. Now remember, the binomial distribution is in the distribution menu on the calculator. So that's a second vars. And then I can just scroll down. We can scroll down and find binomial CDF. Now keep in mind, there's 2 here. PDF gives individual probabilities. CDF gives cumulative probabilities. And that's what we're looking for here. Stats Wizards, I have it turned on here, so it's prompting me for the different values. So the calculator is using the P term, or the P notation. P is the parameter value here, 20%. And let's see, X value is 34. Yes. Press enter, paste, enter one more time. And we see the p-value here is quite small. And one thing to keep in mind now, please don't write the p-value as 1.35. Keep in mind the p-value can never be bigger than 1. That would be bigger than all the probability mass in the whole problem. This is scientific notation. So that E means the exponent in the scientific notation that we would write, the exponent on the 10 would be -4. Another way you can think about this is when you see -4, take the decimal, move it to the left 4 places. 1, 2, 3, 4. So we would have 0.0001 approximately for our p-value. I have to figure out why, or I have to try to figure out a way to toggle between these screens without erasing everything. I'm using PowerPoint here, and I don't know, I have a link to the calculator which works nicely, but for some reason I haven't figured out how to come back. So bear with me, I'll try to figure that out here at some point. Okay, so here's where we're at on the problem. We just calculated the p-value. We found that the p-value is about 0.0001. And that's, let's see, we got the tenths, hundredths, thousandths, 10,000ths. So that's like 1 in 10,000. So what this p-value is telling us is that we'd only see this data one sample out of every 10,000 if the null hypothesis were true. So if our subject was a guesser, then we would only expect them to get at least this many correct, one time in 10,000. Most people are going to say we should reject the null hypothesis or call the data significant with this size p-value. And this realization or this interpretation would mean that or imply that we're going to reject the null hypothesis. Now, just to do what this actual problem says, we're asked to give our decision and we're given the level of significance we should use. And this is the one I like to refer to as the Fisherian alpha. I probably should capitalize A here. It's a proper name. I'm giving it a proper name, the Fisherian alpha at 5%. And this again comes from Ronald Fisher's original textbook on statistics. He just threw it out there as 5%, off the cuff, sort of. But in any case, this has become really one of the main ways people make decisions about whether or not the data are significant or whether or not the null hypothesis should be rejected. And what we can see here is our p-value is well below that 5%. And that would tell us to reject H naught. But the thing to keep in mind is we would be rejecting here for an alpha of 0.01, 0.001, 0.0001, and even 0.00001. Oh wait, sorry, got that wrong. No, that would be too far. That's where we would have to stop. And finally, we have part D, which is to write our hypothesis as a well-written sentence, or state our conclusion. All right, so what is our conclusion? Well, I would write it in a number of sentences. I would start off by saying maybe something like the formal decision is to reject H naught, or I would probably be a bit more specific. Now, I want to put this in a little bit of perspective, though, because I think too often people think about statistical hypothesis testing as methods of proof. And that's not really what we're talking about here at all. What we're really saying is that the data collected are statistically significant. And what does statistical significance mean? Statistical significance means we should pay attention to the data. Oops, let me spell that correctly. And the reason we should pay attention to it is because we would only see data this rare and unusual about once out of every 10,000 experiments. So given everything else about the experiment was done well, there was no researcher bias involved, the cards were shown in a very random or a very appropriate way, randomly, then this data is really probably too unusual to see. But again, it's our own judgment as the consumers of the statistics to make up our own mind. And that's why the p-value is such a useful thing. So by having the p-value, it allows each of us to apply our own standards to the situation. But again, if you're looking at a standard where you have to see data less than 1 in 10,000 times, even a smaller p-value, that's a pretty high standard. Not many situations meet that. So in any case, I hope you found this video helpful.